Good morning, everyone, and thank you for joining us today here in beautiful Florence, Italy, for the 38th International Conference on Software Engineering Education and Training. Today, I am pleased to present our study, Human AI Grading Agreement in Computing Education, a question-level reliability and calibration study. As artificial intelligence becomes increasingly integrated into educational environments, an important question emerges. Can AI-assisted grading produce results that are reliable, fair, and consistent enough for practical educational use? To answer this question, we conducted a large-scale empirical study using question-level grading data collected from real undergraduate computing courses. Rather than relying on anecdotal observations, our work applies rigorous statistical methods to evaluate the agreement, reliability, calibration, and potential bias between AI-generated and human grading. Let's begin. The motivation for this research is straightforward. Across higher education, instructors face an ever-growing grading workload, particularly in large classes and online programs. At the same time, students increasingly expect rapid feedback, often within hours or days rather than weeks. Artificial intelligence offers a promising solution because it can dramatically accelerate grading and feedback generation. However, speed alone is not enough. If AI grading is inconsistent, unfair, or poorly calibrated, its educational value becomes questionable. Therefore, before AI-assisted grading can be adopted on a large scale, educators need strong empirical evidence that these systems are reliable, consistent, and fair. That is the central motivation behind our study. Our study is guided by four primary research questions. First, how closely does AI-assisted grading align with human instructor grading? Second, does that level of agreement remain consistent across different computing courses? Third, can AI maintain accurate calibration across students with different levels of performance? And finally, can AI generate meaningful educational feedback while preserving consistent and reliable grading? These four questions guided both the design of our evaluation framework and the statistical methods used throughout this study. This study makes several important contributions. First, we introduce a practical AI-assisted grading framework that keeps instructors actively involved in the grading process. Second, we provide a large question-level dataset, allowing a much more detailed analysis than studies based only on overall assignment scores. Third, we evaluate human and AI grading agreement using multiple complementary statistical methods, providing a comprehensive assessment of grading performance. Fourth, we examine reliability, calibration, bias, and error patterns together, offering a more complete understanding of AI-assisted grading behavior. Most importantly, our findings provide empirical evidence that can help educators and institutions make informed decisions about the responsible adoption of AI in computing education. This figure illustrates the overall architecture of our AI-assisted grading framework. The process begins with content processing, where assignment materials and relevant metadata are collected. Next, grading rubrics are generated and reviewed by the instructor before evaluation begins. The evaluation stage then uses task-appropriate AI models, selected according to the type of assignment being graded. One important aspect of this framework is that the instructor remains actively involved throughout the entire process, ensuring continuous oversight and quality control. Before results are released, both the final grades and the generated feedback are reviewed. The framework also includes a continuous improvement loop where instructor feedback and performance analytics are used to refine future grading decisions. Overall, this architecture is designed to augment instructors, not replace them. A central design principle of our framework is human in the loop grading. Our goal is not to create a fully autonomous grading system. Instead, instructors remain in control of rubric design, grading criteria, and all final grading decisions. The role of AI is to assist by performing a preliminary evaluation and generating meaningful feedback for students. Before any grade is finalized, the instructor carefully reviews these AI-generated outputs. This approach combines the scalability and efficiency of artificial intelligence with the accountability, expertise, and pedagogical judgment of human educators. We believe this balance is essential for the responsible adoption of AI in education. This slide summarizes the empirical workflow used in our study. The process begins with data collected from real undergraduate computing courses. Each assessment question was evaluated independently by both human instructors and our AI-assisted grading system. The resulting scores were then paired at the individual question level, providing a detailed basis for comparison. Next, we applied a series of statistical analyses to examine agreement, reliability, calibration, bias, and error structure. Finally, we interpreted the findings from both methodological and practical educational perspectives. By following this workflow, we were able to evaluate AI-assisted grading under authentic instructional conditions. The dataset used in this study consisted of 3 undergraduate computing courses. Across these courses, we analyzed 120 assessment questions covering 24 instructional topics. In total, this produced 2,480 paired grading records. Each record contained both a human-assigned score and the corresponding AI-generated score. Rather than evaluating agreement only at the assignment or course level, we performed our analysis at the individual question level. This finer level of granularity provides a much deeper understanding of where human and AI grading agree, where they differ, and why. We believe this question-level perspective is one of the key strengths of our study. Before discussing the results in detail, let's begin with a few key numbers from the study. Our analysis included 2,480 paired grading observations collected from 120 assessment questions across 24 instructional topics. The Pearson correlation between AI and human grading was 0.9591, indicating an exceptionally strong linear relationship. The intraclass correlation coefficient, or ICC, was 0.9517, demonstrating excellent agreement between the two grading approaches. The average grading bias was only 0.0266, showing that the AI neither systematically overgraded nor undergraded student work. Taken together, these results already suggest a very high level of agreement. In the remaining slides, I'll explain what each of these numbers means and how we validated these findings using multiple complementary statistical analyses. The dataset covered a broad range of topics commonly taught in undergraduate computing courses. These included Python programming, object-oriented programming, exception handling, file management, data structures, algorithms, and other advanced programming concepts. This diversity is important because the performance of AI-assisted grading may vary across different subject areas. By including a wide variety of computing topics, we were able to evaluate the robustness and consistency of our grading framework under diverse instructional conditions. The figure on this slide illustrates the frequency distribution of the instructional topics represented in our dataset. To evaluate agreement comprehensively, we use several complementary statistical measures. Pearson correlation measures the strength of the linear relationship between AI-generated and human-assigned scores. The intraclass correlation coefficient, or ICC, evaluates the overall consistency and reliability between the two grading approaches. Weighted kappa measures agreement while accounting for the possibility of chance agreement, making it particularly useful for educational assessment. Mean absolute error, or MAE, quantifies the average difference between AI and human grading. Finally, Bland-Altman analysis allows us to identify systematic bias and evaluate how well the AI remains calibrated across the full range of scores. Rather than relying on a single statistic, using multiple complementary metrics provides a much more complete and reliable assessment of grading performance. The overall agreement between AI-assisted grading and human instructor grading was highly encouraging. The Pearson correlation reached 0.9591, indicating an exceptionally strong relationship between AI-generated and human-assigned scores. The Intraclass correlation coefficient, or ICC, reached 0.9517, a level that is generally considered to represent excellent reliability. Importantly, this high level of agreement remained consistent across multiple courses and different grading contexts. These findings suggest that, when implemented within an appropriate human-in-the-loop framework, AI-assisted grading can closely approximate the grading behavior of experienced instructors. Overall, this represents one of the strongest and most significant findings of our study. These histograms compare the distributions of scores assigned by human instructors and by the AI-assisted grading system. At first glance, the two distributions are remarkably similar. Both exhibit comparable shapes with similar concentrations across the full range of scores. Most observations fall within the moderate to high score range, reflecting consistent grading patterns between the two approaches. This similarity indicates that the AI is not producing substantially different scoring behavior compared with human instructors. Instead, it closely follows the same grading tendencies observed in human evaluations, providing additional evidence of strong agreement between the two grading methods. We also compared the feedback generated by human instructors and by the AI-assisted grading system. One interesting observation was that AI-generated feedback tended to be substantially longer than instructor feedback. In contrast, human comments were generally more concise, often reflecting the practical time constraints faced by instructors. AI-generated comments, however, were typically more detailed and provided additional explanations for the assigned grades. Of course, longer feedback is not necessarily better feedback. However, these results suggest that AI has the potential to provide richer formative guidance while still supporting instructor oversight. An important direction for future research is to investigate how students perceive this additional feedback and whether it contributes to improved learning outcomes. This slide presents one of the most important visualizations in our study. The scatter plot reveals an exceptionally strong linear relationship between AI-generated and human-assigned scores. Notice that most observations cluster very closely around the identity line, indicating a high level of agreement between the two grading approaches. The empirical cumulative distribution function, or ECDF, together with the error analyses, further shows that the differences between AI and human grading remain consistently small across the dataset. Taken together, these visualizations provide compelling evidence that AI-assisted grading closely mirrors instructor grading behavior across a wide range of assessment scores. Next, let's examine grading bias. The average bias observed in our study was only 0.0266. This indicates that, on average, the AI assigned scores that were slightly higher than those given by human instructors. However, the magnitude of this difference was very small. More importantly, we found no evidence of systematic grade inflation that would meaningfully distort grading outcomes. Instead, the results suggest only a modest tendency toward generosity, one that could be further reduced through appropriate calibration procedures. Overall, these findings support the conclusion that AI-assisted grading remains both accurate and well calibrated when used within a human-in-the-loop framework. Next, let's look at calibration. Calibration evaluates whether AI-generated scores remain aligned with human instructor scores across different levels of student performance. As you can see, the calibration curve closely follows the ideal diagonal line. Students who performed well according to human instructors were also identified as high-performing by the AI. Likewise, students with lower levels of performance remained consistently lower performing in the AI evaluations. This indicates that the AI preserved the relative performance differences among students rather than compressing or exaggerating the score distribution. The absence of any substantial calibration drift further strengthens confidence in the practical use of this AI-assisted grading system. This slide examines the performance of our AI-assisted grading framework separately for each course included in the study. As you can see, strong agreement was consistently observed across all 3 undergraduate computing courses. The scatter plots reveal very similar relationships between AI-generated and human-assigned scores, regardless of the course. The error distributions are also highly comparable, indicating stable grading performance across different instructional settings. Importantly, none of the courses showed any meaningful degradation in grading reliability or consistency. Overall, these results suggest that the framework is robust and can maintain reliable performance across multiple instructional contexts within computing education. What do these findings mean for educators? Our results suggest that AI-assisted grading has the potential to significantly reduce instructor grading workload, especially in large or high enrollment courses. Students can also receive feedback much more quickly, supporting a faster and more responsive learning experience. Because AI applies grading criteria systematically, it may also improve the consistency of rubric-based assessment. In addition, this approach offers a practical path towards scaling assessment as class sizes continue to grow. At the same time, our findings do not support removing instructors from the grading process. Instead, they support a collaborative, human-in-the-loop approach where AI enhances efficiency while instructors retain oversight, professional judgment, and final responsibility for grading decisions. Like all research, this study has several limitations. First, our analysis focused exclusively on undergraduate computing education. It is possible that other academic disciplines with different assessment styles may produce different levels of agreement between AI and human grading. In addition, we did not compare AI-assisted grading with the level of agreement among multiple human graders, an important direction for future investigation. The study was also conducted within a single institutional environment, which may limit the generalizability of the findings. Future research should extend this work to additional disciplines, institutions, and broader educational settings. Further investigation is also needed to better understand the long-term impact of AI-assisted grading, particularly on student learning outcomes, engagement, and educational success. In conclusion, our study demonstrates that AI-assisted grading can achieve a remarkably high level of agreement with human instructors. The reliability measures consistently exceeded the thresholds that are widely accepted as indicating strong agreement. Calibration remains stable across different courses, instructional topics, and student performance levels. Although we observed a small positive grading bias, its magnitude was minimal and it did not compromise the overall reliability of the grading system. Most importantly, our findings support the use of AI-assisted grading as a practical and scalable educational tool when implemented within a human-in-the-loop framework, where instructors retain oversight and final responsibility. Thank you very much for your attention.